So let's look at a last example of applying the well-ordering principle, this time to something that we actually care about, a theorem that we. The theorem is the following famous formula for the sum of a geometric sum, for a geometric series or a geometric sum. So the numbers on the left, the powers of r, starting at 1, which is r to the 0, followed by r, which is r to the 1, followed by r squared, up through the nth power of r. You add all those numbers up, and it turns out that there's a nice, simple, fixed formula that doesn't have those 3 dots in it that tells you exactly what the value of that sum is. And the formula, as you can read, is r to the n plus 1 minus 1 is the numerator, and r minus 1 is the denominator. And the claim is that this identity holds for all non-negative integers n, and for all real numbers r that aren't 1, because I don't want the denominator to be 0. So how are we going to prove this? Well, I'm going to prove it by using the well-ordering principle. And let's suppose that this identity didn't hold for some non-negative integer n. So we'll apply the well-ordering principle, and we'll let m be the smallest number n. Where this equality fails, it becomes an inequality. Now, what I know about m immediately is that this equality, if you look at it, when n is 0, the left-hand side comes down to, degenerates to just r to the 0, or 1. The right-hand side, if you check it, is r minus 1 over r minus 1, which is also 1. So equality holds when n is 0, and that means that the least m for which equality doesn't hold has to be positive. So what we know about the least number where this equality fails is that it's positive, and that means in particular, since it's the least one where it fails, if you go down 1 to m minus 1, the equality holds. So we can assume that the sum of the first m powers of r, starting at 0 and ending at r to the m minus 1, is equal to the formula where you plug in m minus 1 for n, and you get that formula on the right, which I'm not going to read to you. Well, we can simplify it a little bit. If you look at the exponent, r to the m minus 1 plus 1 is, after all, just r to the m. So repeating, what I've got is that the sum of those first powers of r up to m minus 1, we can assume is equal to the formula r to the m minus 1 divided by r minus 1, because m failed, and this was the number 1 less where it had to succeed. So now we take the obvious strategy. What I'm interested in is properties of the sum of the powers up to r to the m. Now the left-hand side is the powers up to r to the m minus 1, so there's an obvious strategy for turning the left-hand side into what I'm interested in. Namely, let's add r to the m to both sides. So the left-hand side becomes just the sum that I want, and the right-hand side becomes this messy thing, r to the m minus 1 over r minus 1 plus r to the m. Well, let's just simplify a little bit. Let's put r to the m, put it over the denominator r minus 1, which I do by multiplying it by r minus 1. And then it comes out to be r to the m plus 1 minus r to the m over r minus 1. And I collect terms, and look what I got. I've got the formula r to the m plus 1 minus 1 over r minus 1, which means that the identity that I was originally claiming in fact holds at m, contradicting the assertion that it didn't hold at m. In other words, we've reached a contradiction assuming there was a least place where equality fails. That means there's no counterexample, and the equality holds for all non-negative integers n. So here's the general organization of a well-ordering proof, which we've been using. Let's just sort of summarize it into a kind of a template for proving things. So what you have in mind is that there's some property p of n of non-negative integers. And what you'd like to prove is that it holds for every non-negative integer. So for all n in non-negative integers, p of n holds. And we're going to try to prove this by the well-ordering principle, which means that we're going to define the set of numbers for which p doesn't hold, that is the set of counterexamples, and call that c. So c is the set of non-negative integers for which not p of n holds. Now, by the Well, ordering principle, there's got to be a minimum element, call it M, that's in C. And at this point, the job, by assuming that M is the smallest counterexample, we have to reach a contradiction somehow. Now, up to this second bullet, it's the template. But the third bullet is where the real math starts, and there isn't any template anymore. How you reach a contradiction is by reasoning about properties of P of n, and there's no simple recipe. But the usual organization of the contradiction is one of two kinds. You find a counterexample that's smaller than M. You find a C that's in the set of counterexamples, and C is less than M. That would be a contradiction because M is the smallest thing in C. Or you reach a contradiction by proving that P does hold for M, which means it's not a counterexample. And those are kind of the two standard